A little change in scenery. So I had to go from home to the school, but we're here. Let's continue with this. So we finished talking about positive and negative feedback loops. What I actually want you to do, I want you to pause your video right now, and I want you to find I want you to actually go on and find examples of positive and feedback loops in two areas. So some living feedback loops so from living systems. Don't just do human body, actually do systems like ecosystems as well. So find some living examples and then find some non-living examples and put those up there for yourself, like in your notes, because I know you have some space for those. And then I want you to do that for the negative feedback loops as well. It's fine if you go with body examples, but get something that's from the human body. Obviously it's relatable, but also pull something from an ecosystem. All right, so here we're going to be talking about the different gases. Water vapor are molecules that have pause and do that, and then unpause and then come back. And here we'll be talking about the different gases that are considered GHGs, or greenhouse gases. So water vapor, water vapor is basically molecules that have evaporated off of water, and then they will condense to form clouds. Now they're in the air. Even if they aren't condensed, you can feel the water vapor in the air. But one of the most powerful aspects of water vapor is that they do form clouds. So they will condense around some kind of dust particle or something. So there's an interaction with materials that are blowing up into the atmosphere. Typically it's going to be, like silt or sand, or clay, like particles of rock that have been eroded, and now they're carried in the wind. And so the water will condense around those things, and clouds shade the Earth's surface and reflect incoming solar radiation. Clouds trap outgoing long wave radiation, making the atmosphere warmer. So there's a balance between those two, and we obviously explained that with the positive and negative feedback loops. Carbon dioxide, this makes up 0.037% of today's atmosphere. So it's actually a very small part of our atmosphere, but it's so powerful. Plants use CO2 for photosynthesis, and that is what that's like the pathway in which the atmosphere will enter the biosphere, is through photosynthesis, and it will be locked up in plants, in wood, like in grasses and in the roots. So we'll actually put it down into the roots. But one of the things that you need to understand is that photosynthesis and forests and grasslands are growing all the time. They grow on top of their old growth. And so as they continue to grow, very slowly, there has been a big layer of carbon that has been buried underneath that forest or that grassland or whatever it may be, where that biomass is adding onto biomass, is adding onto biomass. And that has accumulated over millions of years. And so there are fossils of those plants deep under those living things, and those create fossil fuels. There are also layers in the ocean where there's photosynthesis that is taking, right? So diatoms, the phytoplankton is photosynthesizing, and it's locking up CO2 into the body of the little like single-celled photosynthesizing organism. It's going to create its body through the photosynthetic process, and then it's going to die after it reproduces, but it will die, and it will sink into the ocean. And as it falls to the bottom over and over and over and over and over again, those are being layered up. And that creates layer upon layer upon layer upon layer at the bottom of the ocean, also creates an accumulation of biomass that has been happening for millions of years as well. And so there's also fossil fuels under the layers of the ocean. Like when the layers bend, like little gas pockets will form. That's where natural gas comes from. So the ocean is a sink, and it dissolves CO2 because just straight into it, but it also pulls it into that photosynthetic process. The ocean itself as a sink, CO2 just dissolves straight in, like we talked about, like when I was blowing through the straw and you could see the pH change in the bromothymol blue solution. You know that the CO2 is actually dissolving in. So just having gases right up against the ocean, it will pull that CO2 gas into it. And it is a place that is constantly taking on CO2. And because it's being taken out by those photosynthesizers straight out of the water, it's using that CO2. And so it's constantly moving into the ocean, dissolves and releases CO2 with a net gain I'm not even sure what that. Hang on a second. Gigateracarbons? No. I'll have to ask Mr. Item. You guys could be like, what is that unit? All right. I'd have to look it up. But there's a net gain as far as CO2. There's a net gain in the ocean. So it's pulling CO2 off all the time. And that's another aspect that we talk about, these aspects of equilibrium, where the Earth's greenhouse gases should be at a particular level in order to maintain just the right amount of heat so that we can survive. All right, carbon dioxide. I guess I should learn what that is. Gosh, you guys, I don't recognize that unit. Gigatons of carbon a year is what I think it would be. But I will have to, we'll confirm. But humans take out and release 6.5 per year of these of carbon. So you have to look at this unit and just compare. The ocean can take on 2 gigatons of carbon per year, I'm guessing, and humans take out and release 6.5. So we're releasing more than what the ocean is taking on. So that means we have an overabundance of CO2. Pre-industrialization levels of CO2 in the atmosphere were 280 parts per million. The 2001 level of CO2 in the air was 370 parts per million. That's a 30% increase just until that's over 20 years ago. There's a very strong link between CO2 increases and the increase in atmospheric temperature. The idea we want you to see is just that if we are taking CO2 out to use it for fossil fuels, we combust those fossil fuels, what is released in the process? Water vapor, carbon dioxide, and a slew of other things. But the carbon dioxide is re-released into the atmosphere from its captured form. It's been captured for millions of years. And we're just doing this at a higher rate than the ocean can reabsorb it. We're going to end up with a net balance of CO2 in the atmosphere that exceeds that natural level. And we understand that CO2 is already in the atmosphere in very small amounts and is also very powerful as far as a greenhouse gas. All right, change of scenery again. Now I'm out on the field trip. Hopefully you can hear me all right. Other sources of carbon that enter our atmosphere. We talked about carbon dioxide coming, from fossil fuels. The sources of carbon, not just other sources, but sources of carbon in the first place. You see this picture here, like I said, there's going to be a lot of photos that are going to give you examples of what some of these sources are. So burning fossil fuels, whether it be coal, oil, or natural gas. We talked about how coal is formed. I know you might not have picked up on that, but like the burying of forests and the burying of biomass does produce coal beds. If those sit for a really long time, you get oil from that, and animals that are involved in that, like getting buried deep, can produce oil. Natural gas comes more from the oceanic accumulation, but any of those carbon sources that were captured through the process of photosynthesis a long time ago and laid down for long periods of time, and they're held under pressure, now they've shifted and they become something that we can pull out of the ground and burn. So the source of fuel, because it's an awesome human innovation, does give us, though, the product of CO2. And so it's not that burning anything is wrong or bad. It's just that the amount that is coming back into the atmosphere, the rate at which it's happening, is higher because our population is high, because our innovations are really efficient, and because in terms of our own technology, we've developed really awesome ways to efficiently pull fossil fuels out of the ground. The downside to that is that when we use so much of it, we're putting a lot of CO2 into the atmosphere. So this releases CO2. It also releases methane and nitrous oxide. This burning of fossil fuels does account for 97% of all CO2 emissions. And so it's not really about doing away with fossil fuels altogether. It's just that we have to figure out a way to burn less of them and find some other sources, because we know that there's real consequences to that. Other sources of carbon come because of kind of like an indirect source, in that deforestation means that carbon's not being taken in by those living things. It's not being pulled out of the air. And so the ability for the earth to bring that carbon back into the biosphere, if we're cutting down forests, is being interrupted. And so it's also not being stored in the biomass. So deforestation does release the carbon that's in the, in parts of those plant in that plant matter. Even if some of it's used for building, some of it is going to be released in that process. So tropical deforestation accounts for about 20% of the increase in CO2 in the atmosphere, even though that is rather indirect. I mean, obviously, fossil fuels are burned for transportation or for tool use, but just taking away the Earth's ability to bring that CO2 back into the biosphere from the atmosphere does interrupt or does offset this balance, right? Well, the other thing that we have learned is that as the surface of the Earth's average temperature is increasing, it means that there are regions that are no longer permanently frozen. Permafrost is when the ground is permanently frozen. And permafrost can be deep under grounds that become thawed and grow grass, but there may be permafrost a little bit deeper. So, like in the Siberian forest, there's a large amount of CO2 that is being released out of the ground because the permafrost, that there's like regions that are thawing as the earth, the overall average temperature of the earth is increasing just a little bit. And all it takes is 1 degree, right? We know that, like in terms of Fahrenheit, 32 degrees is freezing and 33 is not. And there's going to be a band where temperatures are going to fluctuate when we look at like global arrangement of ecosystems. And the areas that have been permanently frozen are getting smaller and smaller. So permafrost does release carbon as plant matter that has been frozen begins to decompose. Because CO2, as we know, is a product of cellular respiration, and decomposers, they are munching on those on those dead plant matter. And this is a picture here. You can see what kind of the northern areas. This is northern tundra, and they are grasslands, but when they stay frozen, that carbon stays in the ground, or stays in that biomatter. And as they begin to thaw, they do break down and they begin to change over time, and they'll release a lot of CO2, especially in the form of methane. And as you will see, methane is a very, very powerful greenhouse gas. So these are pictures of deforestation, the kind of deforestation that's happening in South American rainforests. Whoops, sorry about that. Um, and then we know CO2 emissions, they've increased 4 times since 1950 through power plants and automobiles, just transportation of goods, so big shipping industries. 30% has increased in the atmosphere, in atmospheric CO2 since the Industrial Revolution began. So we know we can track this. We have those records, and the highest concentration um, is the highest concentration in 650,000 years, especially within the last 150 years. And how do we know what those concentrations were? We actually have records, like those frozen grounds will tell us what the atmospheric temperatures were. So we can take cores of soil and cores of ice and actually piece out, back year by year how much was laid down, and kind of like tree rings, kind of see ice as it accumulates over time. Take these cores. Cores of material, ice, and soil samples, and analyze those and see what those CO2 levels were at that time. We call those proxy measures. They are something that's indirect. Like, we can't obviously go back in time and measure directly what was going on in the atmosphere, but we do have a repository of data that has been collected within the last 100 years, really. But we have that data and we can compare. So we're looking at changes that are really big in terms of percentages. And it is estimated that by 2050, the atmospheric CO2 level will be 2 times what it was before the Industrial Revolution. So we have some things to fix here. You can see that this shows short-term data from like 1960. You can see concentrations increasing, and we know that when we measure temperature, average global temperature alongside that we also see average temperature increase.